functions for representing symmetry operations. So we constructed a very useful tool, namely the projection operator, which allows us to decompose an arbitrary function into its irreducible components. And these irreducible components then transform according to the irreducible representations of the group. So this is an extremely useful tool. One of the uses of group theory is to simplify calculations of matrix elements. And by classifying the basis functions according to the different irreducible representations, we can then simplify a lot the calculations of matrix elements. So let's continue today with this relationship to quantum mechanics. So we, for example, want to calculate matrix elements of Hamiltonian. So this is a typical case where we want to exploit the symmetry of the Hamiltonian. So we want to calculate such matrix elements here in some basis, phi I and phi j. So we want to arrange or construct linear combinations of basis functions such that they transform according to the irreducible representations of the group, of the symmetry group of the Hamiltonian. So in this way, the Hamiltonian will be as diagonal as possible. So we'll show later that if we calculate the matrix elements between two functions or two states that transforms according to the alpha and the beta irreducible representations, then we can show that this is some constants proportional to the alpha beta and delta ij. So the Hamiltonian will be diagonal unless the functions, the basis functions, belong to the same irreducible representations. So we have a definition of symmetry. If a Hamiltonian has a certain symmetry, then that Hamiltonian commutes with the set of symmetry operators that we have here. So that's just saying that the similarity transformations of the Hamiltonian is equal to the Hamiltonian itself. So that's a definition of invariant of the Hamiltonian. Now, the group that is formed by these symmetry operators is usually called the Schrödinger group. It was probably Schrödinger who first studied his equation and a certain symmetry. So nowadays we just call this, symmetry of whatever we have as our object. It doesn't have to be Hamiltonian. It can be some other operators or some other quantities. So let's have a look at this equation here. This equation here more explicitly in the position representation. So let me share a whiteboard. So let's consider operating a symmetry operator on this HR acting on some wave function. So we're working in the position representation. So HR here is something like kinetic energy plus some potential energy. So we assume that the Hamiltonian, of course, has some symmetry represented by these operators here. So now we look at what happens um, to this quantity here when we operate it by a symmetry operator. So according to our definition, this will be just given by this. So we should treat this whole thing here as a function. So we should rotate the coordinates of both of them, of h and the wave function. So by definition, this Hamiltonian is invariant under this symmetry operator. So we are in the coordinate representation and the position representation. So that by definition is equal to HR. So for example, if the potential is spherically symmetric and G is some rotation operator, then we see that rotating the coordinate doesn't change the Hamiltonian, because this is an Abla squared and this is by definition is spherically symmetric. So we have this, and this one here is just T times IR, that's by definition. So then we see that if we put everything on the right hand side, on the left hand side, then we get the following result. So we have not specified what the wave function is. So that means that this thing should be equal to 0. So if we go back to the more abstract operator, then we have the thing that we wrote in the beginning. So I just wanted to do this in a more explicit way to see what is actually happening. But this is a more general definition of symmetry operator. So symmetry is very much related to degeneracy. So I'm talking about the symmetry of the Hamiltonian. It could be also some other operators. So let's focus for the moment on the Hamiltonian. So this is clear from the fact that the symmetry operators commute with the Hamiltonian. So for example, if we take, if we consider the Schrödinger equation, let's say that it is an eigenstate with energy E, then if we do this, so that becomes, so that one acting on that one just give me the energy psi minus h psi, like that. But this is 0. The left hand side is equal to 0 because of this commutativity. Then we see that this quantity, the TG acting on psi, is also an eigenstate of the Hamiltonian. So if I write it like this, you can see that it's also an eigenstate with the same eigenvalue. In other words, this state is degenerate to the state here. Of course, it could happen that this state is just the same as this state. In that case, there is no degeneracy. But in general, this state could be different from this one here. And we have degeneracy. Yes. So symmetry is intimately connected to degeneracy. So whenever we have symmetry, we can kind of expect that there should be some kind of degeneracy in the system. Now, the important point about degeneracy is that the degenerate states of the Hamiltonian can be used as basis functions for an irreducible representation of the group. Let me erase this thing. So degenerate states of H. So let's consider H here as our example form basis for an irreducible representation of the group, of course. And this we can easily understand by the fact that when we operate this on the function, let's say this psi is an eigenstate of the Hamiltonian, so that is equal to this thing, and we know that this is also an eigenstate of the Hamiltonian with the same energy, so it's degenerate. So this means that this can be written. So if I take an I here, take one of the eigenstate, so then that should be expandable as a linear combinations of the other degenerate eigenstates. Yes. Like this. So this means that these degenerate eigenstates form a basis for this representation, and it is generally the representation is irreducible. Generally, but it can happen that it is reducible. There are usually two possibilities. So there is what is called accidental degeneracy in the system. So accidental degeneracy just means that two states have the same energies, but not because they are related by symmetry. So this means that not related not related to symmetry. So we call this accidental. Another possibility, if the group is a subgroup of a larger group, So what do we mean by this? So let's consider an example. I think it will be clear by an example. So let's say that we have a Hamiltonian which is spherically symmetric. So it is invariant under rotation operators. So let's consider the p orbitals. So we're talking about like an atom. So we have p orbitals. So p orbitals then will be like some functions which depends only on the radial distance times the spherical harmonics. the m here. So L here is equal to 1. It's p orbitals. And this is the angular. So this is the spherical harmonics. So the spherical harmonics for L equal to 1 is equivalent to, so this is equivalent to x, y, and z. Yeah. You can form linear combinations of the spherical harmonics, and then you get x, y, and z. So you should divide by r here, but it's just a constant. It's not important. So it transforms according to x, y, and z. Now, if we have a full rotation symmetry, then this, no matter what we do, we always need these three components, x, y, and z. Yes, if we take an arbitrary vector, an arbitrary function in this x, y, z subspace, then if we rotate, we need all these three functions, x, y, and z. It is not possible to reduce the subspace. However, if we only consider rotations about the z-axis, so rotations, so we restrict to rotations about z-axis, then we see that the x and the y will transform among themselves, and also the z. The z will, of course, transform to itself, yes, because we are making a rotation about the z-axis. So then, if we only consider rotations about the z-axis, which is a subgroup of the full rotation group, then we see that these basis functions, x, y, z, they split. Yes. So it means that it's reducible into these two components, two irreducible subspaces. So x and y transform among themselves, and the z transform to itself. Yes, this is what we mean by reducible in this case. So we go back to what we have here. So this is just what I have been talking about just now. So in general, a Hamiltonian possessing a symmetry has degenerate eigenstates, and a set of degenerate eigenstates of H form an invariant subspace and form a basis for the irreducible representation of the symmetry group. So when we do atomic physics, we have we have states like this. So this is atomic state. So we can understand that the irreducible representation alpha actually corresponds to the angular momentum L, and the I here corresponds to the z component of the angular momentum. And the degeneracy is equal to the dimension of the irreducible representation, that is 2L plus 1. So this is actually a general result. So the degeneracy is equal to the dimension of the irreducible representation. So what we have here. Now, as we said in the beginning, that we have this very useful results that arises from symmetry, that if we calculate the matrix elements of Hamiltonian between two states, here phi alpha I and psi beta j, and if they belong to two different irreducible representations, then the matrix elements is 0. In fact, not only if they belong to two different irreducible representations, but even if they belong to the same irreducible representation, it is still 0, this matrix elements, if the rows, we call this the row I and j, are different. So this is a very useful result here. So you can see that if we want to diagonalize Hamiltonian, and if the Hamiltonian has certain symmetries, then we should first figure out how we construct the basis functions in such a way that the Hamiltonian is as diagonal as possible. So we want to sort out the basis functions according to the irreducible representations of the group. And this is where the projections operator comes in, because we can always make a projections on an arbitrary function like this, and that will bring the functions to the irreducible subspace, let's say alpha in this case. So let's see how we show this. This is an important theorem, so we want to show this. So maybe I have a space here. So I have psi I alpha h psi beta j like this. Sometimes I use this different notations. I think this is sometimes used in the group theory book, but this is just the same as this one here. Yeah. So now we can introduce symmetry operator on both sides. So that doesn't do anything to the matrix elements because we do rotations on both sides. This is an overlap or dot product. So if I rotate both functions on both sides, then we don't do anything. So now we make use of the fact that this thing mutes, so that I have h tg like this, and then I use the fact that tg acting on the phi I alpha is just given by sum over, what do I call it? K and L. So we have tki here, alpha, given g, and I have a star because I'm on the left, and then I have t beta, what do I call it? Lj, g, like that. And then I have the matrix elements, which is psi k, alpha, and then h, thing on psi I, beta. Psi L, psi L. Yes, so this one goes with this, and that one goes with that one. Now we can make use of the orthogonality theorem. So this is where the orthogonality comes in again. So we can sum this over G. So let me erase this thing here. So we sum over G. But we have to divide by the number of elements, which is H. So then this whole thing here becomes 1 upon L alpha. So we are using the orthogonality theorem. So that will be orthogonal between K and L and I and J, and between the representation alpha beta times this matrix elements here. Take that like that. So we can continue a little bit here. We can sum over K or L. Then we get need a bit more space here. So that's 1 upon L alpha d alpha beta alpha ij, and sum over K of these matrix elements. Yes, so that is exactly the theorem we want to prove here. So this I can replace this beta with alpha because there is a delta alpha beta anyway. So this is a very useful result here. Yes. So we have a Hamiltonian. We can already diagonalize it, let's say partially. If we choose the basis functions in such a way that they belong to the irreducible representations of the symmetry group of the Hamiltonian. We'll see later that this is actually a special case of what is called the Wigner-Eckart theorem that we will do later. I think we can do it today. I think many of you have studied this Wigner-Eckart theorem in quantum mechanics. So this theorem in quantum mechanics is usually associated with angular momentum states. But actually the theorem is quite general. It is not necessarily related to angular momentum. So it is a more general theorem. But we'll discuss that later. And to do the Wigner-Eckart theorem, we also need to define what is meant by irreducible set of operators. So you notice that before we have t g acting on h and t minus 1g gives us back the Hamiltonian. So this actually implies that the Hamiltonian transforms according to the identity representation. Because it is just one here. H is just H. There is no matrix or anything like that. It's just one. First, let's define what is meant by irreducible set of operators. So this is how we define a set of operators which are irreducible. So we have an operator labeled again by alpha, irreducible representations, and the row I, just like we have for functions. It's labeled by the irreducible representations and the row. So because it's an operator, we have to operate on both sides. Because we recall that if I have an operator A, let's say, we can always write it like ij. Let's say this is, let's say we have some basis functions phi, where this is the matrix elements. So this is phi I. So we know from quantum mechanics that you can write an operator in this form here. So we see that if we make a rotation, then we have to rotate the functions on, or the states on both sides. That's why we have this t and t minus 1 on left and right. Yes. So for an operator, we need both sides. It's not enough to have just one side. Doesn't make sense because it's an operator, so we have states on both sides. So that is defined very much like functions. So we make a rotation like this, then the result is linear combinations of other operators that belong to the same irreducible representation, alpha. So you can compare this with what we have before for the state. So we have Tg acting on, let's say, phi alpha like this. So that is then equal to J phi J alpha T alpha Ji G. So exactly the same form. Yes. So let's consider an example to see what we have here. So we take vector operators like x, y, and z. Then this set of vector operators actually form an irreducible set under rotation. So if we make a rotation, we take one of these, let's say x, then we will find that it's a linear combinations of the other operators. So how do we see this? Let's take an example. So we can see what's going on. So I have it in the notes actually, just to see explicitly what happens. So we take the g, let's say x here, and t to minus 1g. So to evaluate these expressions, then we can just take, say, the expectation value in the position representation. So this is the positioned eigenvectors, because x is a position operator. So now we just use the definition of this operator. So then we get g to the minus 1r because it's acting to the left here. And this gives us g minus 1r like this. So so x is just, we'll pick up the x component of this state. So then we get ex dot g minus 1r. So that's the x component of that vector. And we get minus 1r. Like this. So I can take the g here. So then we get gex dot r. And this thing is just equal to r because we rotate both sides. And this becomes then some coefficients. We don't care what that is, depends on what the g is, but we know that if we rotate a vector in the x direction, then it will be a general linear combination of vector in the other directions. Like this, and then we have dot product with the r, so that is just x plus y ey plus z ez like this times this thing. Yes. So I'm just doing this step by step to illustrate what this rotation of operators means. So then we get ax plus by plus ez just from this 2 dot product times this, and we can put it back. So we get or, and then we write it as an operator now. So you see that this thing is equal to that one, like we said in the beginning. Yes. This is just an explicit example. Okay, so that's a definition of irreducible set of operators. So in quantum mechanics, this would be like the angular momentum, for example, angular momentum operators. So Px, Py, and Pz also form a complete set of irreducible operators, similar to x, y, and z. Okay, so yeah. So now, before we do a Wigner-Eckart theorem, we want to consider what is called the direct product representation of a group. Now we have to differentiate this from what we had before. So before we have a representation of a direct product group. So before we have two different groups and form a direct product of the two groups. And then we have a representation of this direct product group. And the irreducible representation of this direct product group is quite simple because we can just multiply or form a direct product of the each individual of the irreducible representation of the individual groups. But here we are looking at the direct product representation of a group. So we want to know what happens when we multiply. By multiply here, I mean form a direct product between two representations. So we define, this is a definition of a direct product of two matrices, A and B. It's defined in this way. So up here. Yeah. So this is not matrix multiplication, as you can see. So what we have done here, we simply multiply the matrix elements of the two matrices. So we take matrix elements A, I, J and multiply it by the matrix elements of the B matrix, B, I prime, J prime. And that defines a new matrix, which we call A cross B, like that. And we label the row and the columns in this way. It's a combined index, I prime for the row and JJ prime for the column. So one can then form a direct product of two representations, two irreducible representations of a group. And this is important here. So we have a group. We do not have a direct product of two groups. We are talking about a group, and we have different irreducible representations of a group. Yes. So if we form a direct product of two irreducible representations, then that representation, that matrix, T alpha cross beta, is also a representation of the group. But in general, it is reducible. So even when both T alpha and T beta are irreducible. So it is again to be distinguished from the one we had before, where we have a direct product group. So we have two groups, and we form a direct product of these two groups. In that case, the irreducible representation of this direct product group is simply given by the direct product of the two irreducible representations of the two individual groups. But here we have only one group, and we have two different irreducible representations, T alpha and T beta. And if we form a direct product matrix of these two representations, then we can show that it is also a representation of the group, but in general, reducible. Okay, so let's show that in the remaining 5 minutes, and we can have a little break. So this is thing important, so I want to show this. So we have two representation, and we form a direct product representation cross T beta. Sometimes it's just written with a cross without the circle, but doesn't matter. It's just a notation. So now we want to show that this is a representation of the group. So let's take particular group element. So let's call it G1. So I'm following the notes. But we do this step by step so we understand what we're talking about. So we take another group element G2 and we look at the particular matrix elements. So II prime and JJ prime. So this is equal to the matrix multiplications. So we need two indices. The I prime here, and then K prime G1. So I'm looking at the matrix multiplication of these two. Beta K prime, and then JJ prime. Yes, so you're with me, yes? So we're multiplying two matrices. So now we just use the definitions of this direct product. So that is equal to T alpha IK. So we take that for the first matrix. And then the T beta I prime K prime G1 also. So I'm looking at this matrix here. So that becomes this matrix multiplications. Not the matrix multiplication, but just a product of the elements. Yes. And the same for the other ones, so that we get Kj, G2, and T beta K prime, J prime, G2. Yeah. So we haven't done anything, we just use the definition of the direct product matrix. So now we can form the multiplication between this one and that one, because we sum over K. So that's just a matrix multiplication. So then we get T alpha becomes Ij, and that's G1, G2. And for the beta, we have similar thing. We have I prime, some multiply these two. You get G prime, and again G1, G2. Well, but these are just a definition of direct product. I prime, j prime of G1, G2. So we show that this direct product matrix is also a representation of the group. Yes, it's quite straightforward. It's just writing out the definition of the direct product matrix, and you can show that it is also a representation. So let's see, it's already 11, but I can continue a little bit, just very short here. So we can show then that the character of this direct product representation is simply given by the product of the characters of the individual representations. So this is by definition equal to, right, like that. So it's very easy to see that these are just T alpha I by definition, and that is T beta I prime I prime. So each of these is just the trace or the character. So the character can be easily calculated by just multiplying the characters of the individual representations. It is very useful formula here, which can be then used to decompose the representations later. Okay, it's a good time to have a little break here. We can start again at, let's say, 11:15. So if you have questions about what we've been talking about or about other things. If not, then we start again at 11:15. Okay.
Faraday.
So let's continue. So everybody's back. So we've been talking about direct product representations. So one can ask, what are the functions that transform according to these representations, to these direct product representations? So it turns out that the functions that transform according to the direct product representation is just direct product of the functions corresponding to the individual representations. So if psi I psi alpha I transforms a set of psi alpha I transform according to representation T alpha, and another set of functions, I call it phi JB. So the other set of functions can be completely different from the first one. So again, I would like to emphasize that the important point is how the functions transform, not the form of the functions themselves. So the functions can be arbitrary. The important property is that they transform according to the irreducible representations. So if we have these two sets of functions, psi alpha I and phi beta j, that transform according to the irreducible representation T alpha and T beta, then the direct products of these functions transform according to the direct product representation T alpha beta. So let's show that. That's quite straightforward, actually. So let me erase that one. So I have this product. So let's operate it on an arbitrary symmetry operator, TG. So in the node, I use the same function phi, but in general, it can be an arbitrary function. So I do it in a more general case. So I have phi and I have psi and phi. Yes, they can be completely different functions. So now we just use the fact that these psi alpha I transform according to the irreducible representation alpha. So then I can write it as a sum over k, say, psi k alpha here, and then I have ki alpha g, like that. And the same for the phi beta j, so that's sum over phi L then beta T beta Lj G, like this. Now we can just regroup this thing. So it's sum over KL. I have psi of K, then put them together, bracket. Then we see that that T alpha Ki times T beta Lj. So it's the definition of the direct product representation, the direct product matrix. So that is just by definition is equal to G, like this. So we see that these products form a representation of symmetry operator. So this is exactly the same form as for this, for example. So that is just sum over J. Yes, sum over J, and here we have sum over KL. So KL is our indices. Now, in general, this direct product representation is reducible. There is no reason why it should not be reducible. So we can then find some unitary matrix, I call it U, that bring the representation into a block form. Because that's what we mean by reducible. So this direct product representation can be decomposed into the irreducible representation, and M gamma here tells us how many times the same gamma representation appears in the reductions of the matrix T alpha cross beta. So if we go back to what we have here, so we see something like this. I don't know why do I call this. I should have a tilde here. Tilde. It's a different matrix, of course. For some reason it disappears from my PDF. So yeah, so it's like this. Yes. So I perform similarity transformations on the direct product matrix T alpha beta, T alpha cross beta by the matrix U. Then that matrix is brought into a block form. Yeah, so this is the block form here, and this is 0, 0. So each of this is a matrix, and it's a matrix. So this is just an example, and so on. So for example, the representation representation A appears twice. Yeah. So we have TA and another TA. We have a representation B appears 3 times, and so on. So that's what the multiplicity tells us, M gamma here. So to calculate these coefficients, it's quite straightforward, because all we have to do is just compute the character. So we know that the character of the alpha cos beta here is given by k alpha times chi beta, like that. And so we can decompose this. And to calculate these coefficients, we just use the first orthogonality relations. So this thing is then given by it's 1 upon h, sum over the class, and the number of class, I alpha, ck, so beta, ck, and we pick up particular reducible representation, gamma, let's say. So we have to take a star there, and ck like this. So this is the general formula that we had before, that allows us to decompose the direct product representation into the irreducible components. Yes. So this m gamma then tells us how many times the representation gamma appears in the direct product representation. Now, this direct product representation is actually something that we also do in quantum mechanics. So when we add two angular momenta, so we form total angular momenta. This is exactly what we do. So we've been discussing this in a rather general term. We have two functions or two states, psi alpha I and phi beta j, like this. And then we form a direct product of this. So we have a set of alpha and phi beta j, like this. So in angular momentum theory, when we add to angular momentum, this is exactly what we have. So we have, so this would correspond to some J1, M1, and this would be, usually use that notation of J2, M2, like this. So we have two angular momentum states, J1, M1, and J2, M2. So the J here is just the alpha, or let's take J1 alpha, and J2 is beta, and the I then corresponds to the M1, and the J corresponds to, sorry, not J, but where's my pen here? Okay, the M2. So J corresponds to the M2. What am I doing here? J. Okay. Confused here. No, it's correct. It's okay. So we have this correspondence. Yes. So this is what we have in the quantum mechanics when we do angular momentum theory and we add to angular momenta. We have the states and we form a direct product of these. And these matrix, this matrix U here, this unitary matrix, is actually just the Clebsch-Gordan coefficients. So they're just called the Clebsch-Gordan coefficients. So let's look at this from a kind of opposite point of view. Instead of looking at this from the representations, we can also look at it from the basis, yes, from the product states. So let's do that. Right, yeah. So we have these product functions, psi I alpha and phi beta j. So we know from what we had last week that we can always decompose given functions into their irreducible components. Yes. So if we take a particular product like this, we can always decompose the functions into the irreducible components like that. And M here denotes the possibility that you can have more than one irreducible representation. Same representation can appear more than once. So that corresponds to when we expand it like this. So this M corresponds to that M. Yes. So let me just explain this better maybe. So if I have this diagonal form like that. This is the alpha, and this is another the alpha, and this is the beta, and so on. So we see that the subspace, we look at the subspace, then these functions here transforms according to the alpha representation, but also this one according to the alpha representations. So if I'm given an arbitrary function, then it can be decomposed into the same irreducible representations several times. This is what we mean by this M here. So now we can then write this functions in terms of the basis functions, this capital psi, of the irreducible representations. So we have capital psi gamma, okay, which forms a basis for the irreducible representation gamma. And M again denotes the multiplicity. That's the same representation. And this then just the coefficients. So these coefficients are just the Clebsch-Gordan coefficients. That is. So if we choose these bases here to be some linear combinations of these product functions using the U matrix that we had before, then this U matrix is just identical to the Clebsch-Gordan coefficients. So I've been looking at this from two different point of view. Yes, before we look at it from the matrix itself, from the representations, and we look for a unitary matrix that transforms the matrix into a block form, so that is the U matrix. But now here we are looking at the functions, the product functions, and we look at the coefficients. See, as a linear combinations of basis functions that transform according to the irreducible representation gamma. And so this is exactly what we have when we add angular momentum. So let's go back here. So in the case of angular momentum, we have M1. So I'm trying to illustrate this with what we know from quantum mechanics. So we just write it like this. So this is the same as G1, M1 cross G2, M2. Yes. So when we add angular momentum, we want to form linear combinations of these products such that the linear combinations are eigenstates of J squared and the total angular momentum, yes, Jz, like this, total. So J here would be J1 plus J2. And this is exactly what we have in this case, but it's a more general form. So we have products of the states psi alpha I and phi beta j. As we said before, this alpha corresponds to J1 and I corresponds to M1 and so on. The J2 and J2, M2. So the mathematical structure is identical. So if you recall that the total angular momentum states, we call it the capital GM like this, is a linear combinations of these of this product and the coefficient is given by the Clebsch-Gordan coefficients. So this is a function of J1, J2, M1, M2 in general. So this is exactly the same Clebsch-Gordan coefficients that we have here. So it's just a matrix that rotates the bases such that the resulting new basis functions transform according to the irreducible representations of the group. So we form linear combinations of these product functions. So we have this. So we have linear combinations of these functions, called capital like that. So that with M here. And this is ij, alpha 5 beta j, and this is the Clebsch-Gordan coefficient Cij, gamma mk. Oh, okay, I write it in a different way. So this is my u, but it's the same as the c. So this c is written like this. So it's just linear combinations of these products such that the resulting new bases transform according to the irreducible representations. Okay, and this Clebsch-Gordan coefficients usually normalize. So when we sum over ij, take this thing here, okay, and this is equal to 1. But that's just a convention, so we normalize it. So actually, in angular momentum theory, these Clebsch-Gordan coefficients are chosen to be real. And it's also unitary. So C is unitary. So now we can do the Wigner-Eckart theorem. Let me see what I have here. Yeah, the Wigner-Eckart theorem. So the Wigner-Eckart theorem can be understood in terms of these decompositions of product representations into their irreducible components. So we want to calculate in general matrix elements of this type here. So we have some sets of irreducible vectors, operators, not vectors, or alpha I. And we have two functions or two states which transform according to irreducible representation gamma and beta. And the Wigner-Eckart theorem tells us that this is just proportional to the Clebsch-Gordan coefficients. So the basic principle is actually quite simple. Let's go through this basic principle first, and then we go through the more detail. So the idea is that if we think of this state of I as a state, you can think of it as a state. So this is actually transformed according to the direct product representations. So we can show this later. Okay, I will show this later. So this transform according to T of cross beta. So then it's kind of clear that these set of functions can be decomposed into their irreducible components, yes, like we just did. And it's clear then that if the components do not have component belonging to gamma, then this matrix element will be zero. So for this matrix element to be non-zero, one of the irreducible representation, or one of the irreducible component, of this function should transform according to representation gamma. So that is the basic principle. We could also work, we could also take this one. We can also take this one as our state, and we say that we decompose this into irreducible components, and that must contain representation beta. It's the same thing, yes, but we usually operate to the right, kind of psychologically. More uncomfortable to operate to the right, but we could have operated to the left. So let's show that this state here transform according to the product representation. So it's difficult to do. So I have it in the notes. So let's take a particular element, symmetry element operation. And I call this phi ij. So phi ij here is just this function or state, yes. So that is equal to J I beta J. So again, I would like to emphasize that what's important is not this F here, but rather this thing, this beta and the J, the labels beta and J, which are important, because it tells us that that function transforms according to the beta representation. So I can just introduce here t times t to the minus 1. So then we get tg by t to the minus 1. Okay, I put the other way around. That, and I put t, g, acting on state f like that. So according to our definition, this is a set of irreducible operators. So that becomes sum over k. So that's it transforms according to representation of R. That's a linear combination. the other operators in the same irreducible set. And that thing is just use the definition of the irreducible representations. It's the linear combinations of functions in the irreducible subspace. So we say that we can regroup this. Yeah, Km, I have alpha k and then beta m. So all of these are numbers except the operator. So I write it like this, and this times that one, well, that is just a direct product representation. So that's a direct product matrix, I mean. So Km I j g. And this thing is what we call psi m. So that shows that these products transform according to the direct product representations when we perform the symmetry operation on them. So that we can expand these product functions into its reducible components. Like, so we can write psi j in terms of its irreducible component, call it chi gamma prime, and like that. And the Clebsch-Gordan coefficient. There are various ways of writing the Clebsch-Gordan coefficient, so this is not necessarily a standard way. It's just my own notation here. We just have to keep in mind that in other books it may be different. Everybody seems to have their own favorite way of writing the Clebsch-Gordan coefficients. So these are just the Clebsch-Gordan coefficients. So now we will calculate the matrix element. So we look at gamma I beta j. So then I just plug in this here. Then we get some gamma prime k prime m j prime k prime c gamma prime k prime I j m. So just to remind you that this m is again this multiplicity of the same irreducible representation. So we can now use the fact that if I have two functions which belong to two different irreducible representations, then they are orthogonal. So this means that when we sum over gamma and gamma prime and k prime, then it picks up the value of gamma prime equal to gamma and k prime equal to k. So we just left sum over m. Okay. Like this, and gamma ij m. So this is the Wigner-Eckart theorem. So this matrix elements here is usually written in this way. Alpha, alpha, yeah. like this, just a notation. Yeah. But the point is that it does not depend on the I and the j. So independent of ij, that is the Wigner-Eckart theorem. So the Wigner-Eckart theorem is kind of nice because it factorizes these matrix elements into a part which depends entirely on the symmetry. So this is the Clebsch-Gordan coefficients. So we have seen that the Clebsch-Gordan coefficients don't care about what the functions are as long as they transform according to certain irreducible representations. So this is entirely dependent on the symmetry. Whereas this part here depends on the actual form of the functions. So you can see that depends. When we calculate these matrix elements, it will depends on what is this f and what is this capital psi. So they contain the usually called the dynamics of the systems, like the potential, the actual form of the potential. So if you think of it as wave functions, then of course this f and the capital gamma depends on the actual form of the potentials. But as long as the potential satisfy a given symmetry, that dependence on the symmetry is contained here in the Clebsch-Gordan coefficients. So the parts which do not depend on symmetry, like the strength of the potential or some other parameters, so that dependence enters here in this so-called reduced matrix element. Reduced matrix element. So we see that the Clebsch, not the Clebsch, but the Wigner-Eckart theorem that we learn in quantum mechanics is kind of a special case of the more general theorem or general results. So in quantum mechanics, usually we talk about the Wigner-Eckart theorem in terms of the angular momentum states. So these two are angular momentum states, and this is the so-called spherical tensors. But the theorem is actually more general, as we have seen here. So now coming back to the result we had before for the Hamiltonian. So we see that we have dg h t minus 1 g is equal to h. We are assuming that the Hamiltonian has a symmetry represented by these operators. Then if we compare this with a more general definition of the irreducible set of operators, j t over j I, like this, then we recognize that this is just the representation corresponding to this Hamiltonian is just the identity representation. So the identity representation means that all this t is equal to 1. So if this is equal to 1, then I just get back to the operator. So we can understand the results that we had before. And that if I take the matrix elements, the Hamiltonian between two different states, the different irreducible representation, then it becomes some coefficient C. This is not the Clebsch-Gordan, but some other coefficients. So let me call it A, maybe coefficient A, delta alpha beta, and delta ij. So we could have just written this down immediately from the Wigner-Eckart theorem. So let's see, what time is it now? It's only 5 minutes left. But okay, so we can consider a few kind of generic applications of group theory. So basically, the, the applications of group theory rely on these decompositions of product functions or product of an operator and a function into their irreducible components. So one useful application is related to what is called selection rules. So this is basically just the Wigner-Eckart theorem. Selection rules. So very often we want to compute matrix elements. So let's just take an example. So let's say that we want to compute optical transitions. So we have a electronic system like an atom or a molecule, and we shine light on it, photons coming in, and we'll look at the outgoing photons and see how much is absorbed. And this we're looking at the optical transitions. So these optical transitions are governed by vector operators. So example here, optical transitions. Not transmit. Transition. This the operator is this vector operators x, y, and z, called the dipole operators. So we want to compute transitions between two states. So let's call it final, some operator, and initial states, like that. And this O here is one of these, or linear combinations of those operators. So let's say that we have considered this D3 symmetry. Just to give a concrete example, let's say that the system could be a molecule that has a D3 symmetry. Then we can figure out which final states we have a coupling to the initial state, which is a non-zero coupling that couples initial and final state for these dipole operators. So let's say, just for simplicity, we assume that the initial state transformed according to the identity representation. Yes, so just take a simple example. So that this product here transforms according to the dipole operators, which is a vector operators. So the dipole operators, which are vector operators, we have seen before in the example that we did previously, that this breaks up into the representation T2 and T3. Yes, you can go back and look at the example. So now we have this representation here, T2 plus T3. That's representing this dipole operator, which are vector operators. Then we want to multiply this by the identity representation, which is the T1. So this is the identity representation of the initial state. Yeah. So this is easy because T1 is just 1. So then this is just equal to T2 plus T3. Yes. So this tells us that the final states, psi f, must transform according to one of these representations, either according to T2 or T3. So if the function does not transform according to any of these representations, then this matrix element will be 0. So it's kind of nice because we don't have to do anything. We just look at the symmetry, and then that tells us which matrix elements are 0 or not. If the initial state it does not transform according to the identity, so let's say that it is something else. Let's say it transforms according to different states. Let's say T2. Yeah. Then we just have to figure out what is the T2 times T2. So this will be some linear combinations of the representation like this. So we just calculate the trace and then use the first orthogonality relations to figure out the coefficients m gamma, and the same for the T3. So we do this one by one. So this will also be a sum over, let's say, alpha. So then the final state must be one of these representations, which are contained in these two product representations. So the principle, I think, is quite simple. It's just a matter of decomposing a given product into its irreducible components. Yeah. So this is one use of the Wigner-Eckart theorem, sometimes also called selection rules, because it selects which states one can go into, which states is coupled to the initial state. And that depends, of course, on the operator. And we can have a more complicated operators. You can have powers like this, this kind of operators, and so on. They also form a set of irreducible operators. But the principle is the same. Yeah. We just have to decompose. So the keyword is decompose. Products, states, and operators into the irreducible components. Okay, so a bit over time. Maybe that's not a bad time. Maybe not the bad time to stop. We can just continue next time on Thursday with some more concrete examples. So next time we will consider Bloch theorem. So this is a theorem, famous theorem when you study crystals. And then we will also consider one major applications of group theory, namely analyzing normal modes, so the normal modes of vibrations in molecules and solids. Okay, so let me stop here. So are there any questions you would like to ask? So I have put up the exercise problems. And I will also put up the assignments, the home assignments soon.
I have a question.
Yes.
More or less regarding, because I took the quantum course this spring. And then when we were talking about this, I started looking in the lecture notes for that course.
Yes.
And when we do just the regular transformation if we have two angular momentum states, and then we go to use Clebsch-Gordan to go to like the
Yes.
big J and M.
Yes.
Then it says here that the representation for this rotation group or a rotation with a big J is irreducible.
Irreducible, yes.
But isn't it? Maybe I'm just a bit confused. I'm just a bit confused because it's.
Yeah.
Isn't it in a block form?
Yes. So let's see.
Or is anything that's in a block form then
Yeah.
reducible?
So it's like this. Yes.
Exactly.
This is like this, exactly like this. Yeah. So you have this product of two angular momentum states. Yes.
Yeah.
And you can then use the Clebsch-Gordan coefficients. So this is just, I can write it the other way around. Yes, I can write.
Yeah, exactly.
Yeah,
Just,
the psi, yeah, like this. Yes. So this is my Clebsch-Gordan. Clebsch-Gordan. It's the same thing.
Yeah.
So I form linear combinations of this product of two angular momentum states, such that this thing is now the total angular momentum states.
Yeah.
Because it transforms according to the representation gamma, which is the capital J. The capital J. Yeah.
Exactly.
Yeah. So if we use this, then the rotation operator will be in the block form.
Yeah.
Whereas if we use this basis, it will be kind of scrambled. There is no.
Yeah, exactly. It would just be everywhere.
Yeah. So it's really identical to this. This is a more general, more general way of looking at these things. Yeah.
That makes sense. Thank you.
Good. Any more questions? Okay, if not, then we just see again. Let's see each other again on Thursday. Okay. Goodbye now then.